Welcome back, AP Statistics. We're going to start our last section of Chapter 7 with a misconception about regression lines. This silly plots regression line can be used to estimate the grumpiness index, apparently measured from 0 to 100. If you didn't know that, now you know, given hours of precious sleep. However, it cannot be used to predict hours of sleep given a grumpiness index. We need a new regression line for that. Well, what does that mean? What that means is we can predict from our regression line that given 7 hours of sleep, your grumpiness index is going to be somewhere around 65 or 66, okay? But if you want to say, okay, what amount of sleep would I need to have a grumpiness index of 70? I guess that would be like 6.5. That's not a good use of the regression line. It doesn't go both ways like that. Why is that? It seems like an odd quirk there. Let me explain. Recall that the regression line is in this form. Y hat equals some constant plus some constant times x. You got your B0 and your B1, and that B1 is equal to R S sub y over S sub x, all right? And this is the most important part. Then for x hat, predicted values of x, B1 is equal to, oh, that's a little switcheroo. And it's a really frustrating switcheroo because notice that this and this are not the same unless the standard deviations of your two variables are the same, which is very rare. You're never going to find that. Notice that they are not the same, nor are they reciprocals. S sub y over S sub x is the reciprocal of S sub x over S sub y, but you throw that r in there, and these fractions are not reciprocals of each other. That is why you need to generate a new regression equation to predict sleep given a grumpiness index, to predict x values given y values. So here's an example that puts everything we've learned in Chapter 7 together. Even if you hit the fast food joints for lunch, you should have a good breakfast. Nutritionists concerned about empty calories in breakfast cereals recorded facts about 77 cereals, including their calories per serving and sugar content in grams. Question: how can we use sugar content to estimate calories in breakfast cereals? Well, this is a many-part process because we are given a pretty broad question. How can we use the sugar content to estimate calories? Is there a relationship that would allow us to input sugar content and estimate calories? So, does the regression line meet the conditions? That's the first thing we need to consider. If we were to put a regression line through these data, would it meet a set of conditions? Is there a set of quantitative variables we're assessing? Well, yes. The variables are quantitative, sugar is measured in grams, calories are measured in, well, calories. Linear pattern. Is there a linear pattern? It does seem like the data are up and to the right. This is real world data, so it's not surprising. It's more of a cloud than a line, but there is an up and to the right trend. No outliers. I don't see any really clear outliers. There is this cluster at the bottom here that's a little off the beaten path. There are some values up here, but no clear outliers. And no pattern in the residuals. Now, we don't have a residuals plot, unfortunately, and we don't have a set of data to plot the residuals for. But a good way to check to see if there's a pattern in the residuals is if we were to draw a regression line, would there be an even distribution above and below the line? And I would argue that there is. You fit a regression line through that, there's going to be about the same number of points above and below. No fanning pattern, nothing interesting going on there. So, given r is equal to 0.564, not bad, compute the equation of the regression line. Okay, so we have calories and sugar and some sample statistics about those 77 cereals. What you're going to do is use these two formulas, and you are going to find the regression line that uses sugar to predict the number of calories. Feel free to try this on your own. Unpause the video when you are done. Okay, I'll assume we're ready to continue. First, we want to compute B1 because we need that for B sub 0, if you recall. B1, we substitute 0.564 for R. The standard deviation for the Y variable is 19.5, and the standard deviation for the X variable is 4.4. So we get about 2.4995. I rounded to 4 places. And now we can take that value for B1, substitute it in here, substitute the X bar, which is 7, and substitute the Y bar, which is 107. And we would get 89.5032. So that is your regression line. Now we're going to describe what the model is saying. We want to talk about B sub 0 if it's relevant, and B sub 1, which is always relevant. Okay? So B sub 0 is actually relevant in this problem. Why? Because it is possible for your cereal to have no sugar content. That is possible. So the model predicts that we can expect a sugar-free cereal to have about blank calories per serving. Well, if you substitute 0 for sugar, you're predicting about 89.5 calories per serving. And then the model predicts that we can expect an increase of, so we're talking about increase or decrease, that's the slope, that's B1. 2.4995 calories in a serving per additional gram of sugar. Now note, I included the magic words, the model predicts. The model predicts. If you don't have those magic words or words like them, then you are using deterministic language, okay? The word expect is another thing. We come in with expectations, not guarantees, all right? So there's no deterministic language that we are using in these problems because this is not a deterministic equation. It's a regression line used for predictive purposes only. Numbers 4 and 5. Given R equals 0.564, determine the proportion of the variation of calorie count explained by, think variation accounted for, by the variation of sugar content. All right? So this is variation accounted for. So what proportion of the variability of calories is accounted for by the variation of sugar content? How is the variability of the Y variable accounted for by the variation of the X variable? Well, that is an assessment of R squared. So we would take R and we would square it and we would get that number, about 31.81%. All right, I chose to put it in percent. That's how it's often given, but you could put it in decimal. It just seemed to flow a little better in this sentence to make it a percent. Number 5, the standard error of the data set is about 16.2. Interpret this result. Take a moment, see if you can interpret this standard error, which we also called, and I like this name a little better personally, typical residual size. Okay, so take a moment, see if you can interpret this 16.2 number that you're given. Okay, I'll assume we're ready to continue. Here's how we would interpret it. The mean residual size for our data is 16.2. All right, so on average, the data points are going to be 16.2, and our units would be whatever the Y units would be. The Y units would be calories. So 16.2 calories off the beaten path of the regression line, right? So the mean residual size for our data is 16.2, and might be nice to include that these are in calories. Just some closing notes here. Reading output from statistics software periodically over the course of the year, we're going to be shown something that looks like this, or you're going to have to interpret something that looks like this. Your calculator has a particular interface, and computer software has generally an interface that would look something like this. Okay, so you want to be familiar with several ways of displaying outcomes in statistics. So from this table, that's this guy over here, we can infer the dependent or response variable is total fat, and the independent or explanatory variable is protein. Now, where are those located? Well, up here it says dependent variable is. Well, that's a clear sign. There's your y variable. That's those are the values we are predicting using the regression line. Our input is down here, all right? It's under the variable column, all right? This is the predictor, or the x variable, right? Now, b sub 0 is equal to that. B sub 1 is equal to this. So we can form a regression line predicting total fat given inputs of protein, okay? So how do we find those values? Well, we see that across from intercept is 0.63. Wow, I can't say numbers. 0.683077. That's our b sub 0 value. B sub 0 is a y-intercept in the take on slope intercept form that is the regression line. So it is not surprising that we see it next to intercept. And then b sub 1 is going to be across from protein. Okay, so this b sub 1 right here, that's how we get that number. And then we can conveniently plug it into a regression line. Bada bing, bada boom. All right, third thing we can notice, about 69% of the variation in total fat is accounted for in the variation of protein. How do I get that? Well, r squared is given right beneath the dependent variable. This is our variation accounted for. 69% of the variation in my y variable, total fat, is accounted for by the variation of protein. As protein varies, total fat varies, and a lot of that, and nearly 70%, is explained variation. Okay, so that's how we find that. Standard error, or typical residual size, is 9.277. How do we find that? Well, just like the calculator, it's right next to S. There it is. And here's your homework.